so there's just one more result we need to be able to say that we proved all theorems about operators, elliptic operators, which we use to construct the Hodge decomposition and prove other properties for elliptic complexes. As we have sorry. Suppose we have a self-adjoint elliptic operator. Let's set H equal the kernel of G. Sorry, the kernel of D. Then there is a green operator G. Such that such that we have this. Okay, now I don't claim anything else about G. I don't claim that it's a differential operator. It's some C linear map from section to section. In fact, it will this operator G will be an operator of order 0, meaning it will have all Sobolev extensions from W something to W something, but we won't need this, and so that's less improvement. Okay, now the green operator, where do we get? Well, what did we just prove? We just proved that the we just proved that the space of sections is the kernel of D plus the kernel of D star plus plus the image of D. Well, this was in. Let's see which part of the notes it was. I think the very first part. Let me check. Uh, uh, okay, like this. Okay, we proved that the image of D is the kernel of D. Okay, so we more precisely we proved that the image of D is the kernel of the complement, but this implies this because the kernel is the kernel of the kernel of D star is finite dimensional. Okay, Floyd, does this make any sense?
Well, yes, it seems so.
This is the theorem we proved, or the proposition we proved out today, and it's not for free. But once we have it, since the kernel is the kernel of the is finite dimensional, we have this decomposition. The kernel of D star is finite dimensional. We have this decomposition. Okay, now what else? What else? So this is this is something which is which we have in general for an elliptic operator from C infinity of v to C infinity of v. Now let's recall that the operator is elliptic, so elliptic and self-adjoint. Now, since the operator is self-adjoint, we may as well write the kernel of D instead of the kernel of D star. And so I define I define the operator G as follows. On the kernel D, I take it to be 0, and on the image of D, I take it to be D minus 1. Well, D minus 1 normally doesn't make sense, but we have an element. We want to take D minus 1 of Y, and Y is inside the image of D. So Y does have at least one preimage under D, and it has exactly one preimage. Let me write this. Every Y inside D and this preimage is can be chosen in can be chosen in the orthogonal complement of the image, because the direct sum of Curti and the orthogonal complement is the whole space of sections. Which follows from the fact that the dimension of the kernel of D is less than infinity. So the preimage is there is a preimage in the orthogonal complement of the kernel, and this is the same as the image, which we just mentioned. Okay. Now the preimage exists, and the preimage exists, and it was also unique. Why is it unique? Well, it is unique because well, if two elements in the image of D go to the same element under D, then the differences in the kernel, but the image of D does not intersect the kernel. So the map defined here makes sense, and it's straightforward to check both equalities. For example, if we apply D first and G next to XY, we get sorry. Right. Okay, so so we apply D first. What do we get? We get 0 dy. Then we get 0 d minus 1 dy, which is 0 y. And the other way around, it works just the same. That's y. This is inside here. This is inside here. Goes to 0 d minus 1 of y. This is g. This is d, and the result is 0 d minus 1 of y, which is 0 y. Okay, so in both cases, I I get the orthogonal projection to the complement to the complement. The orthogonal projection to the orthogonal projection to the image of D. But this is the same as the orthogonal projection. Sorry, 1 minus the orthogonal projection to the kernel of D, which is 1 minus the orthogonal projection to H. Okay, well, this is what we wanted to prove. let's see. Blah, 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 blah. Yes. Okay, so this was relatively easy, but the really well, the real theorem was this one, the kernel of G star orthogonal complement is the image of B. Once we have this, the remaining existence of the green operator is straightforward. Okay, are there any questions? Okay, let's see. Let's prove another fact from analysis, which we used last week. Well, let's at least state this fact, and then we'll see whether or not we feel up to proving it. So suppose we have suppose we have a compact operator from a Hilbert space to itself. Then the kernel and co-kernel of the identity plus A are finite dimensional. Okay, Leonid, do you remember this this statement?
Yes, it was last time.
Yes, we used it last time, so it wasn't just the theorem. We used the statement, and so my suggestion is to prove it, because well, that's all things being equal. Let's let's prove it now because then we'll move on to other things and forget about it. What do you think?
What I think about what?
About the plan to prove this statement. And by the way, Volodya and Simon, same question.
Well, I have no objections.
Yeah, me too.
Okay.
Okay, well, let's try to prove this. In other words, we want to prove that if I have a compact operator, then the identity plus the operator is Fredholm. Well, first of all, let's prove that the kernel is finite dimensional. Okay, let me change here. Plus to minus. It will. This will result in the rest being slightly slightly neater. In the sense that there will be less minuses afterwards. Of course, it doesn't matter because if the kernel if A is compact, then minus A is compact and vice versa. Okay, so let's prove this this problem. So first of all, let's see. So the kernel of I minus A is invariant under A. And on this space, the operator A is compact. It's compact because if it's globally compact, then it's also a compact operator when restricted to any subspace. But it's also invertible. And in fact, it's not invertible. It's the identity operator. Not only invertible. It's exactly equal to the identity operator. Why? Well, because because the kernel of I minus A is precisely the space of all x, such that AX is equal to X. And so the kernel is finite dimensional because otherwise the identity would not be compact. So the identity operator would not be compact. Okay, we're running out of time again, so I'll save the notes and we will let's finish the proof after we restart the session. Meanwhile, are there any questions? Vladimir, why is it impossible for the identity operator to be compact if the underlying Hilbert space is not finite dimensional?